Hello, I am Shashank, and in this video, I will be presenting my study project for the advanced data mining course. The focus of my project is on analyzing chess games using a rich dataset of over 20,000 matches. Chess, being a perfect information strategy based game, provides a great ground for pattern mining, player behavior analysis, and predictive modeling. So, let me begin by walking you through the structure of the dataset. Each row represents a single chess game and includes several attributes. These can be broadly grouped into the following: game metadata, which includes fields like ID, rated, created at, turns, and so on. Player information includes player ID and their ratings. Move data tells us about the moves played in a game. And opening strategy contains information related to the opening used by the players. Now that we have understood the dataset, let's move on to the workflow. The pipeline of the project consists of four major stages: pre-processing and exploratory data analysis, clustering algorithms, community detection, and classification and prediction. The first step was to pre-process the data. This included handling missing values, converting timestamp formats, and converting move sequences into a structured format suitable for downstream analysis. I also conducted exploratory data analysis to understand the distribution trends, such as how often certain openings appear, which player color wins more often, and which victory conditions are most frequent. After pre-processing, I applied clustering to group similar types of games together. I used four clustering algorithms: k-means, agglomerative, Gaussian mixture models, and db-scan. Each of these methods help in revealing different aspects of the game groupings. The details of their behavior and evaluation metrics will be discussed in the later section. Once the clusters were formed, I applied community detection techniques to discover latent structures and relationships, especially among players with similar patterns in moves or strategies. This step helps highlighting recurring behavioral communities within the dataset. And finally, I built a predictive model to predict the next move. So for this, I used a voting-based ensemble approach combining three classification algorithms: naive-Bayes, decision tree, and logistic regression. The aim was to predict the next best move from a given sequence of previous moves. The majority voting system ensures robustness by aggregating the strengths of each classifier. Now, I'll take you through the code for this project. First up, we have the pre-processing phase. Once the data is loaded, the first step is to convert the timestamp columns from milliseconds to human-readable datetime objects. This allows us to compute game durations and perform temporal analysis. Next, I calculate the total game duration in seconds using the time difference between the last move and the game creation time. I also engineer a new feature called rating diff, which gives us the ELO rating difference between the white and black moves. This new feature helps identify whether high-rated players tend to win more frequently and if rating gaps affect game dynamics. After that, I drop irrelevant columns such as game ID, player usernames, and raw moves column. So this raw moves column will be processed separately later for the prediction task. Finally, I performed a sanity check on the game duration to clean up any invalid or non-finite values. This pre-processing pipeline ensures that we start with a clean, structured, and feature-rich data for the next stages like clustering and communication. Then, after pre-processing, I performed exploratory data analysis to gain a better understanding of the patterns in the dataset. We start by looking at how games typically end. This bar chart shows the victory status distribution. We can see that resignation is the most common way the games end, followed by checkmate and timeout, and few by draw or event. This gives us insight into player behavior. Most players prefer resigning over playing till checkmate. Next, I plotted the winner distribution. This shows a nearly balanced spread between white and black victories, though white has a slight edge, which aligns with common chess knowledge that playing white and going first can offer a small strategic advantage. Then I analyzed how long games typically last using a log scale on the x-axis. So we observe that while most games are short, especially bullet and blitz formats, there's a long tail of longer games, likely representing rapid or classical formats. And one of the more insightful visualizations is the relationship between rating difference and win. This plot shows that when white's rating is significantly higher, they tend to win more. And similarly for black, when the difference is negative. Games with near zero rating difference tend to be more balanced and show a higher chance of. And finally, I examined the top 10 most frequently played openings. This chart reveals that openings like Van Kerge's opening are surprisingly common, followed by Sicilian defense and its border attack variation. We also see other established openings such as Scotch game, French defense, Caro-Can defense, and Philidor defense appearing in the top 10. Different variations of Queen's Pawn game like the Chigorin variation and Mason attack also feature prominently, indicating the popularity of solid and classical games, classical opening structures. This suggests that while some less common openings see frequent play in this dataset, well-known theoretical lines remain a significant part of players' opening choices. We now move into clustering. This section is aimed at grouping similar games together based on certain features. The goal is to uncover latent structures or styles within games that might not be immediately obvious. We start by selecting the features. These features reflect game dynamics, that is, how long games last, how many turns they take, rating disparity, and opening depth. Then we apply one-hot encoding to the categorical features, which allows us to incorporate categorical variables like victory status and winner into our numerical clustering process. And before clustering, we also standardize the features and apply PCA for 2D visualization. While PCA is not used during clustering itself, it's helpful for plotting the results in a lower dimensional space. So I have compared 4 clustering algorithms: K-means, agglomerative, Gaussian mixture model, and dbScan. Each of these algorithms explores the clusters in different ways, that is partitioning, hierarchical, probabilistic, and density based. So here is a comparison of the cluster distributions across the various algorithms. And each subplot shows how the algorithm divided the games. These plots provide visual intuition about how well each algorithm separates the data. To evaluate how well these algorithms perform, we looked at 3 key metrics. First is the Silhouette score, where higher values indicate better defined and well separated clusters. Second is the Kalinske-Harabaz index, which also favors higher scores for well dispersed between cluster distances and tight within cluster groupings. Finally, we have the Davis-Golden index, where low scores are better as it measures the average similarity between each cluster and its more similar name. Now, looking at these results across the metrics, K-means and agglomerative clustering stood out as top performers. They show nearly identical and favorable scores across all 3 indices, suggesting that they created clusters that are both well separated from each other and internally cohesive. Gaussian mixture model, on the other hand, showed slightly lower scores, particularly for the Silhouette and the Kalinske-Harabaz index. This hints that the underlying assumption of Gaussian-shaped clusters might not perfectly align with the data structure of the dataset. dbScan identified 8 clusters, which could be insightful. However, it yielded the highest Davis-Golden index, indicating that its clusters were relatively less well separated compared to K-means and agglomerative. Its Silhouette and Kalinske-Harabaz scores were also lower. Therefore, for the next stages of our analysis and for labeling of our data points, we primarily focused on the results of K-means clustering algorithm. It provided us with clean and interpretable partitions, making it a strong foundation for further investigation. We now move into uncovering latent clusters of players, or what we call communities. To do this, we used the Louvain method, which is a fast and popular community detection algorithm optimized for modularity. We begin by constructing player profiles that capture two key features: the average elo rating of the player and their most frequently played opening. We combine the data for both white and black games and sample 3,000 unique players to keep the network manageable for visualization. To convert categorical openings into numerical form, we apply label encoding, which allows us to treat openings as a feature in similarity computation. Next, we standardize the player features and compute cosine similarity across the players. Using these similarity scores, we build an undirected graph where each node is a player and each node connects a player to their top 10 most similar players weighted by the similarity score. This results in a dense, informative network where each edge represents strategic similarity. With the graph in place, we run the Louvain algorithm, which iteratively optimizes the modularity to detect community structures. Each detected community is a cluster of players who are closely linked in terms of their preferences and playing style. So now we can visualize the Louvain communities based on the sample 3,000 players. Here, each color represents a different community, visually highlighting the distinct things that we have identified. Think of each dot or node as a player. The lines connecting them, the edges, are denser within communities, indicating a higher degree of similarity in their playing patterns. The layout of this network is spring-based. This means the players with more similar structures are pulled closer together, giving us a spatial representation of these organic groups. This visual provides a compelling picture of the natural clustering that exists within the chess world. We can see some communities appearing as tightly knit clusters, suggesting strong similarities among their members, while others are more loosely connected, indicating a wider range of play styles within the group. Let us now delve into some of the most prominent communities that we've identified and see what their characteristics reveal. Now, community 25 comprises of 122 members with an average elo of approximately 135. Interestingly, their most frequently played openings is the Vant Kurges opening, followed by Sicilian defense and the Baudelaire attack variation of the Sicilian defense. This suggests a group of players who lean towards less conventional openings, often surprising their opponents early in the game. Next, we have the community number 2 with 98 players and average elo of around 1,294. Their top opening is the King's Pawn game, Wayward Queen attack, along with other King's Pawn game variations. This could indicate a segment of players at a lower rating range who favor aggressive early queen deployments. Community 8 is a notably stronger group with 95 members and a significantly higher elo of roughly 1,835. Their most common opening is the French defense, knight variation, followed by the Indian game and Hungarian opening. This aligns with a more advanced player base and that prefers deep strategic openings requiring a solid understanding of chess. And we also and then we have community 15 that consists of 93 members with an average elo of about 1233. Their openings include modern defense and King's Pawn game, which again pointing towards less mainstream choices. So this community might represent experimental or more casual players who deviate from standard openings. So this kind of detailed analysis of these communities give us valuable insight into how playing styles, opening preferences, and skill levels are interconnected. We can observe distinct behavioral communities naturally forming within the chess landscape, each with its own unique fingerprint defined by their playing habits and expertise. In this final part of our project, we focus on building a predictive model that suggests the best next move in a chess game, given the move history so far. But before we jump into move recommendation, let's talk about how we frame this as a classification task. We use a supervised setup where The input is given as a sequence of past moves from each game, and the target is the game winner, either white or black. By learning from complete games, we aim to model the kinds of moves that contribute towards a player eventually winning and use this to infer what kind of next move is favorable in a given situation. We take a 10% sample from the full dataset to speed up training, that is around 38,000 games. We filter out draws and missing data, and then using count vectorizer, we convert the uh, moves column into a bag of words model, that is move frequencies. This gives us a sparse vector representation for each game's move sequence. We trained and evaluated three models on this data. The first is multinomial naive Bayes, which gave us an accuracy of 70%, and it performs well due to the bag of words assumptions. Strong balance between precision and recall is found, and it predicts both white and black wins well. Next, we have decision tree with a depth of 20 and a minimum split of 10, which gave us an accuracy of 54%. It tends to overfit the sparse high dimensional input, and the performance is noticeably weaker, especially for predicting black wins. And finally, we have logistic regression, which gave us an accuracy of 66%, which is more robust than the decision tree, but underperforms Naive Bayes. It predicts both classes fairly, but slightly favors white wins. Now, these results support using the naive Bayes as a primary engine for the next move predictor, while also including others in an ensemble setup. We use a pre-selected set of 20 popular candidate moves and simulate each one being the next. For each candidate, we append the move to the input sequence, run all three models to compute the probability of winner being the current player in the turn, and each model votes for its most confident move. We use a majority voting system across all three classifiers, and in case of ties, we break it using average probability confidence. Finally, we have integrated this into an interactive app using Gradio. So here we can see the interface. The user, let's say, inputs a partial move sequence such as this, and once we click on submit, the app predicts the best next move, that is X3, with a confidence of 0.75. So this wraps up our exploration into chess analytics using classical machine learning, data mining, and network-based methods. Thank you.